everyone, welcome to the video. In this video we are going to study the effect of noise in AM receiver. The effect of noise in AM receiver. So let's begin. So when I am talking about the noise in AM receiver, the analysis we perform here is an amplitude modulated system using envelope detector. The demodulator here is that we use as a demodulator in the basic receiver block diagram will be replaced by envelope detector. Correct? So, in a full AM signal, both sideband and the carrier waves are transmitted, which is represented by the equation of AM, where S of t is the equation for modulated signal. AC is the amplitude of the carrier cos omega ct, where omega c is my angular frequency of carrier and m of t is my message signal. This is the equation for AM signal that was transmitted by the transmitter. Here K is a constant that determines the percentage modulation, right? So the block diagram, as we see in the previous video, that S of t is my modulated signal, which is transmitted from the transmitter end, but in the channel the white noise is being added to the transmitted signal, and at the receiver we receive a signal which contains my modulated signal with white noise. Then this signal is passed through a band pass filter and produce an output x of t, where my x of t contains the modulated signal S of t with a narrowband signal n of t, right? This wideband noise is narrowed to n of t. Then this composite signal is passed through an envelope detector which produces an output y of t. Now if I look at the equation, if I look at the modulated equation, my signal power would be, this contains two components. One is AC cos omega ct, and the second component is Ka AC cos omega ct into m of t, right? These are the two components in this signal, correct? So if I found the power of this signal, it will have the average power of this signal. First factor is AC square by 2, and the average power of second signal is Ka square AC square by 2 into P, where P is the average power of m of t. So I can write that my signal power is AC square by 2 into 1 plus Ka square into P, right? Now if I have to calculate the noise power, it would be N naught by 2 into B, where B is the bandwidth, correct? So my signal to noise ratio at the front end of the receiver or at the input of the receiver becomes AC square into 1 plus Ka square into P by N naught into B. I hope I am clear up to here, right? Now this signal is passed through a band pass filter, produces an output x of t, right? I can write x of t is nothing but s of t and n of t, correct? Now what is s of t? S of t I have written here, this is AC plus AC into Ka of m of t, right? Plus n of t. N of t being a narrowband noise can be expressed as in phase and quadrature component. The same thing I have written here, that it is n of t can be written as ni of t cos omega ct minus nq of t into sine omega ct. This we have already seen in the previous lectures. Correct. Now what is y of t? Y of t is nothing but the envelope of x of t, right? And how do we write envelope? It is the under root, the term cos square, the factor with the cos factor whole square plus nq of t, right? This is the envelope of this x of t. Now looking at this equation, this first factor is much greater than my nq of t. So we can neglect this term. If we can neglect this term, so I can write this equation like AC plus AC into Ka into m of t plus Ni of t. Now you'll see that my output y of t contains the first factor this and the second factor is noise signal, right? Now again, see this equation here, one factor is this and second factor is of noise, right? My one factor is this and second factor is of noise. Now look at this first factor. This is AC plus AC into K into MT, correct? Okay. In this term AC is nothing but a DC factor. Right? This is a DC component which can be neglected by passing this signal through a capacitor. If I apply a capacitor here, I will get only this signal, right? This would be neglected or blocked by the capacitor because it is a DC component. Now if I look at this signal, what would be my signal component? This is my signal component, AC into K into MT, right? And what is my noise component? Ni of T is my noise component. So again, if I have to find the signal power in this composite signal, I would write it as P times AC square into Ka square. Okay, what I have written here is the same. Now what is the noise power of this Ni of T? It is N naught into B, that we already derived in the previous videos, N naught into B. Now if I have to find the figure of merit, what would I do? I would calculate the signal to noise ratio output divided by the signal to noise ratio at the input. So here you will find that the signal to noise ratio at the output is, the ratio of this is Ka square into P divided by 1 plus Ka square into P. So you may found that the signal to noise ratio is always less than unity. So we can say that noise performance of an AM receiver is always inferior. Noise performance of an AM receiver is always inferior to that of DSP-SC receiver. Thank you for watching my video.